I'm just going to make a couple of announcements. One, just a reminder, our next seminar is going to be on December 2nd, and it'll be given by Stephanie Crabtree. So we'll be going into the land of archaeology. So that'll be a little twist. The cats are doing dangerous things. And yeah, so just a reminder that this talk is being recorded. So during the Q&A, if you don't want to be on the recording, just make sure to turn your video and your microphone off, and you can write a question into the chat. But if you don't mind, then it would be great for us to have an informal sort of question and answer discussion after the talk. And feel free to talk amongst yourselves in the chat during the seminar as well. Just a reminder, this is a informal talk. We just want everybody to be really nice and have a good time. So please do that. And thanks for being here. Okay, so without further ado, we have a really awesome speaker today. And I'm very, very excited about this talk. I love like how this seminar has really kind of gone all over the place in terms of fields, and Guillermo García-Pérez is just like this amazing researcher of all kinds and a very interesting person as well. And he's a senior researcher of theoretical physics at the University of Turku in Finland. And today he'll be talking to us about emergent spatial entanglement in many body quantum systems. So Guillermo, I'll let you take it away.
Yeah, thanks very much for the nice introduction. Let me just share the screen. 1 second. Okay, so hi everybody, and thank you very much also for attending. I'm really excited to be talking here today. And yeah, I'm a researcher at University of Turku. But by the way, can you see my the mouse?
Yeah.
Can I use the point? Okay. So yeah, I'm a researcher at University of Turku, and recently I've also become the chief scientific officer of Algorithmic, which is a startup in quantum computing. And well, what I'm going to talk about is this topic of emergent spatial entanglement, and essentially it's networks of correlations. So this is it's networks of quantum systems, and because I'm assuming that this is a complex systems audience, the backgrounds are very heterogeneous. So I've decided that I will give a brief introduction to entanglement to explain what it is, so that we know what it is before we start talking about it. But first, I'll give you a little bit of background on like my story, so that you know where I come from. So I'm from Barcelona. I was born there, and I studied there my bachelor and my master's thesis as well. And then I did my PhD there with Maria Àngels and Maria Àngels Serrano and Maria Boguñá. And the topic was complex networks. It was the sorry, just give me a second, because I have this screen which is like okay. For some reason it was blinking. So my PhD thesis was on complex networks, in particular in this field of network geometry, in which one tries to understand the topology of real networks in terms of geometry, and this geometry in turn models the similarity space between the nodes. And it's a very fascinating topic. I'm still working on it. I still collaborate with a group in Barcelona. But then, while I was there in Barcelona doing my PhD, I came to Turku for a research visit for a few months, and I fell in love with the place. I really like Finland, and I also liked very much the topic. It was more, it was quantum. I was still working on networks, but quantum networks. And I was offered a postdoc position after I finished my PhD, so I came here. And here I've been in the University of Turku in the group of Sabrina Maniscalco, and who is actually moving now to University of Helsinki. And I've also been a researcher at the Complex Systems Research Group here in the math department. So I belong to both departments, physics and math. And in my time here, I've been working in a number of topics. And one of them is the coherence and this quantum to classical transition, in which essentially what we're trying to do there is to understand. So when you have a quantum system that interacts with its environment, the interaction with the environment leads the system to lose the quantumness, all the quantum properties. This is called the coherence. But at the same time, this same phenomenon, this same dynamics explains how the information about the state of the system, in a way, diffuses into the environment in a way that the observers measuring the environment agree on the state of the system. So this process leads to the emergence of objective reality, which is something that is not for granted. It's not given for granted in quantum physics. That doesn't seem to be very consistent with our classical reality. So I will use classical as opposed to quantum. This is usually what it means. Another topic has been quantum computing and quantum simulation. So using quantum computers to simulate quantum systems, which was the original motivation for using quantum computers at all. And this has led directly to founding this company, Algorithmic. And then the third, overall topic is complex quantum networks, which are essentially networks in which the nodes are quantum systems, and then the links can represent different things. They can represent, for example, interactions between them, or they can represent correlations. And actually, I'm underlining here the one that corresponds to what I will be talking about. I will talk about precisely this second class, and in which the correlations are entanglement. So let me then introduce entanglement. So before I introduce entanglement, so entanglement is a quantum correlation. And as such, I need to introduce first some quantum system before I can talk about correlations between quantum systems. So I will introduce maybe the simplest, and also is the one that we will study later on, which is the spin. And the spin is this intrinsic magnetic moment or angular momentum of some quantum particles, like, for example, electrons. So this means that these electrons, you can regard them as being little magnets, or having attached to them a little magnet, if you like. That in principle is a vector that can be oriented in any direction in space, a priori. But the funny thing, if you like, is that when you try to measure the orientation of this arrow, so this vector in space, so you try to determine the different components of this vector, for example, X, Y, and Z, quantum phenomena start to appear. And we have to understand this. So in particular, the first thing that happens is that if you try to measure, for example, the vertical component of this vector, it turns out that experimentally you realize that only two outcomes are possible. So in principle, one would expect that because this is a vector and it can be oriented in any way, if you measure the vertical component of this vector, you could get a continuum, a spectrum of values that could be from being completely vertically oriented to being completely oriented pointing down and somewhere in between. But this is not the case. You only get two outcomes for this component. One that represents the spin partly pointing up or pointing down. And this is already puzzling, but then there are more things that will become apparent later. And to explain all these things, because it might be a little complicated if I start talking about how you measure, and I want to abstract a little bit from the physics itself and explore all this in a more abstract way. So I've decided to use this kind of a graphical language in which I represent different things with these elements that you can see in the screen. And I'm separating things into three classes. One of them is the state, which is, say, the object is this kind of a rounded box here, is the mathematical object, if you like, that describes our knowledge to some extent of the system, or essentially what we can predict about the outcomes of measurements. Then there is the measurement, which is this fancy looking arrow, which represents the experiment in which we measure something in whatever way. And because the measurement, we are talking about the spin that could be measured, we could be measuring the vertical component of the vector or one of the horizontal components. What I'm doing is I'm drawing here an arrow inside that represents the direction along which we are performing the measurement. So the component of the vector that we are determining, the vertical one in this case. And then there are the outcomes, which are these arrows without any box around. And here I'm showing, for example, is essentially the phenomenon. So you have, say, a class of spins, for example, electrons that come from the same source, and you don't know anything about their state. So I'm drawing here a question mark that means I don't know anything about it. And then we measure them one after the other in the vertical direction. And as I said, only two outcomes are possible, up or down. And they happen with some probability P or 1 minus P. If I instead measure them in the horizontal direction, I will only get left or right. So the spin partly oriented towards the left or towards the right, if you like, with some other probabilities. Now, this is phenomenological. This is what happens. The question is, to what extent, because there is some randomness in all this, to what extent can we predict? here I'm saying that there is some probabilities for the outcomes, but I'm also saying, okay, we don't know anything about the original state. So to what extent this randomness here comes from the fact that I don't know anything. This is what we are going to explore next. So we're going to do it in the following way. Suppose that I take the spin that I didn't know anything about, I measured it in the vertical direction, and I picked one. So this, when I measure, I can get up or down as outcomes. So say that I pick one for which the outcome was up. Now the question I'm considering is, what happens if I measure it again in the vertical direction? So if I measure this component again, will I get something random again, or will it be well-defined? Well, in this case, it is a well-defined property. So I will repeat the measurement and get again the outcome up with probability 1. So now I can say, and of course, if I repeat the same measurement over and over again, unless anything happens to the spin in the meantime, this is the outcome. So now I can say, or I can decide to say that this spin is in the state up, which for me, all I'm saying is now the state of the spin is such that if I measure it if I measure the vertical component, I will get the outcome up with probability 1. This is all I'm saying. But now let's go on and let's think, how about the other components of the vector? Let's try to determine them. Say that now I take the spin, which was measured in this state up, so that I know that the vertical direction would yield the outcome up, and I measure it now in the horizontal direction. Well, it turns out that in this case, the outcome of left or right have probability 1/2. Okay, now to what extent is this a property of the fact that, say, a consequence of the fact that I didn't know anything about the original state? So I only determined the vertical component of the spin, and it could be oriented in any other direction in the perpendicular, say. How can we address this? Well, let's do the following. Now I take out of these spins that some of them yield outcome left and some of them yield outcome right, I pick one or several which yield the outcome left. So now I know that if I measure it again if I measure again the horizontal component, I will get left as outcome with probability 1. This is the same as we saw before for the vertical one. But now the question is, now I know the horizontal component, which is left, but how about the vertical one? If I now measure the vertical one, what do I get? Do I get also up with probability 1? Because I already knew now that it was up before. But this is not the case. If I now measure in the vertical direction, I get up or down with probability 1/2 again. So in a way, at this point here, when I knew that the horizontal component was left, I erased completely the information regarding the vertical direction. It became, say, not defined at all, unpredictable. And now after I measure the vertical one and I get, for example, the outcome up, the same thing will be true about the horizontal one. I will have lost the information about the horizontal component. So this is the way it is. I mean, this is not a theory. This has been confirmed by numerous experiments and observations, and this forces us to admit that perpendicular spin components are complementary physical quantities. So you can at most one of them can be defined. So you can have maximal certainty about one of the directions, but that will imply automatically complete uncertainty about the perpendiculars. It's like what you've heard about the particles not having at the same time a well-defined momentum or velocity and position. It's a manifestation of the same. But so far, we've seen only one single spin. Now, what I want to address is how correlated can the outcomes of the measurements of the spins can be for more than one spin. So say that we have two spins, how correlated can the outcomes be? And to address this, we will consider the following setup in which we have three people, Alice, Bob, and Charlie. These are the names for A, B, and C in quantum information literature. They always put these names. And essentially, Charlie has a bag full of spins that he can pick and he can modify. He can prepare any state he wants. He can, for example, decide to prepare a couple of spins in the state up or down or left or right. He can do that. And what they want to do is they want to get Charlie to prepare pairs of spins such that one of them will be sent to Alice and the other one will be sent to Bob. And Alice and Bob will measure the corresponding spins and they want the outcomes to be correlated. So Charlie proceeds in the following way, which we will call the classical way, and you will see why this is not quantum later on. What he does is first he tosses a coin, and if he gets the outcome heads, he takes 2 spins and he prepares them in the state up. If he gets tails, he prepares them in state down. So then obviously when they are sent to Alice and Bob, when they measure in the vertical direction, if the state that Charlie prepared was up, then they will both observe outcomes up and up. If he prepared down, then Alice and Bob will both agree that the outcome is down. So the marginal distributions of the outcomes, of course, this is repeated many times. And Alice and Bob only measure every spin once, then they throw them away, and then they pick the next pair prepared by Charlie. They will agree that the marginal distribution for each one of them, for only Alice or only Bob, is completely random. They get up and down with probability 50-50, but there is a perfect correlation. So this is good. They have achieved correlation. But now they consider what happens when Alice and Bob measure in the horizontal direction. And in this case, what they observe is that the outcomes are completely uncorrelated. They get left, 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 right, right, left, and right, right with equal probability. So the marginal distributions are still maximally random, but so is the joint one. Why does this happen? Well, here when Charlie prepared the states, he prepared 2 spins independently in the same state up. But as I said before, if we measure one of these spins in the horizontal direction, we get left or right with probability 1/2. And these probabilities are independent for these 2 states. They've been prepared independently by Charlie. So this breaks completely the correlation. So this is to say, this state that has been prepared, say, with a coin classically, are correlated, but only along one direction, and the perpendicular directions are not correlated at all. But now Charlie proceeds to correlate them in the quantum way. And the quantum way is the following. He starts taking 2 spins and preparing them in some known state, that in this case is up and up. It could be anything, but let's simplify. It's up and up. And then he brings them together and he lets them interact. So there is some interaction, physical interaction between the 2 spins. Now, it's not like before that he prepared them independently. Now they interact. And after letting them interact for a while, then the state of the spins becomes this joint state, which we cannot notice that I've removed the arrows here, because the arrows meant that we could predict the outcome along that direction. And in this case, we cannot predict the outcome in the state that that Charlie has prepared. We cannot predict the outcome of any of the 2 spins separately. There's nothing to be predicted. But when they are sent to Alice and Bob and they measure in the vertical direction, they both agree. They always get up, up, or down, down. So it's perfectly correlated. But also if they measure in the horizontal direction, now they are correlated and they get left, left, or right, right. And this actually happens along any direction they choose, even if it's some intermediate direction. Of course, everything I've said here doesn't mean that they have to be exactly the same. So depending on the state that Charlie prepares, it might be that, for example, the measurement along the vertical direction on Alice's apparatus is correlated with the horizontal one in Bob's. So this can be tweaked in a way. And the same for the previous setup. What's important is that in this case, the correlation occurs in many directions. As long as both rotate the apparatus, the measurement apparatus the same way, the correlation persists. So this extra correlation that we see, before we had correlation only in one direction and now it's in a whole family of directions, is called entanglement. Well, entanglement is also referred to the notion, the fact that the state cannot be written separately. We cannot write the state of the 2 spins as 2 separate states, but it's only one thing. And what's important is that it requires quantum interaction. You cannot prepare them independently or communicating and sending, like preparing the state just correlated in a classical way, just by regular communication. So now that we know a bit what entanglement is, we can consider the networks of entanglement. So obviously now entanglement networks will be networks in which the nodes represent spins. And here I'm writing 2-level systems because it doesn't really need to be spins. It could be any quantum system that has 2 degrees of freedom, that the outcomes can be two values. For example, a quantum bit can have outcome 0, 1. This is also a 2-level system, and everything I said is also valid for this class of this class of systems. They're mathematically equivalent. And well, in these networks, the weighted links represent this pairwise entanglement as quantified by a quantity called concurrence. And concurrence is a number between 0 and 1 that quantifies how entangled the 2 spins are. And here you have an example of this network, which only 5 nodes, and you see the values of the concurrence here. Actually, here they go from 0 to 0. Less than 3. This is actually an experimental result on a quantum computer, and okay, they shouldn't be 1 because actually in this kind of states they cannot be 1, but they should be a bit higher in any way. But this is what the networks are. Now there is the question of why considering these pairwise networks at all. So okay, I think given the audience, I don't need to motivate why studying things in terms of networks. But in the quantum physics community, it's not so easy to get them interested, say, in network representations of physical systems, even if they are intrinsically complex. They realize they are complex, but in a way, it's like the networks don't tell them anything. So this is something we have to work on. But let me motivate this in a say experimental, well, not only experimental, but let me consider this in terms of the quantification of the complexity of the system itself. If you have a quantum system with n particles, for example, like n spins, the state, the object, mathematical object that describes the state of the system, is a density operator. It's a matrix that is very large. It has exponentially many numbers in the number of particles that you consider. So this is obviously unfeasible. You cannot really treat this amount of information as soon as you have a few, or say a relatively small number of spins. You cannot even treat these numbers. So just representing the density matrix or the density operator requires a huge amount of memory. It requires, of course, a lot of calculations if you have to really, say, deal with that many numbers, but also inferring the state. So determining, given a quantum system, an experimental physical system, what is the quantum state of that system requires exponentially many measurements. So it's unfeasible. There's no way one can do it. In exists the possibility of recovering the state of a quantum system. It's called state tomography, but in practice becomes unfeasible very soon. What we propose instead is, and there is one point also, which probably you will agree with, which is that even if you had the technical capabilities of dealing with all this huge amount of information, there is still a question of what do you extract from it? What is useful information in all this? This happens often in complex systems. You have huge amounts of data, but then finding the right representation that gives you something useful is not that trivial. So in this case, what we are saying is, yeah, even if there is lots of information in the system, let's start by reconstructing only the information that I want to look at. And let's say that I only care about these pairwise correlators, or pairwise correlations. What I could do if I wanted to reconstruct this is to reconstruct not the whole quantum state of all these many, well, here is only 5, but not the n spins, but only pairs of spins. So the state of the spins 0 and 1 alone, as if nothing else existed, between 0 and 2, 0, 3, and 1 and 2, 1 and 3, 1 and 4, and so on. This would be one of these density operators per pair of spins. But because there's only 2 spins, the dimension of this thing is relatively small. It's a small matrix. And there are only n squared of them, as 1 per pair of spins. So this is still, this is much more reasonable. This is just like a regular network. Instead of having 1 number per link, now we would have a matrix, but that's all. It's still feasible, small matrix. And the problem, well, pairwise tomography now, so doing the tomography of all these states is feasible, but still a bit heavy because the experiments really take time. So in this case, we still have a quadratic amount of measurements to be done. So one of our result is a method, an algorithm, to perform the measurements on all these qubits or spins, that it's exponentially faster. So you can reconstruct all these objects in only a logarithmic amount of measurements. And the trick is essentially that when you are you're measuring so you're inferring the state between 0 and 1, you're measuring properties of 0 and 1. At the same time, you can parallelize, and you can also measure properties of 0 and 2, because you're measuring 0 in any case. So in a way, you parallelize the measurement of many spins at once by measuring, like it's arranging the measurements in the proper way. And once you have all these row ij's, you can compute the concurrence, which is this line. But you can compute other things as well. This is why, in this, I'm just going a bit off topic, but just to explain a little bit this in the context of the current state of the literature. So here you have this multiplex. It's actually coming from the same paper as before. So once you reconstruct these pairwise density matrices, you can represent the concurrence, which is this layer here, but you can calculate other things as well, pairwise quantities. Like, for example, mutual information that contains not only entanglement, but all the correlations as well, or discord, which are some other kinds of quantum correlations. You can compute many things. And then in principle, one could study these multiplexes and hopefully retrieve more information about the state of the system that you could just by looking at the entanglement. This is something to be done. But what I wanted to show is that for now, the only works that have been have addressed at all the idea of a network of entanglement or correlations, I would say are these three mostly. In these two, they studied networks of both concurrence and mutual information for critical spin chains. So systems like the one I will explain later. And essentially what they saw is that the network properties are critical so these systems have exhibit phase transitions, quantum phase transitions, and the network measures are also sensitive to the phase transition. And this one by Sean Carroll and other people, what they're looking at is networks of mutual information in states that have some nice properties in which this actually represents the entanglement as well. But what they realize is that they have geometric properties. So that you can see these networks as being discretizations of some manifolds. And actually they follow dynamical behaviors. When you perturb the amount of entanglement, the resulting network is perturbed in a way that seems consistent with gravity, with general relativity. So it's even establishing connections with quantum gravity, which is a very interesting line. But okay, now let's move into the actual results. I don't know how am I doing in time. Yeah, as well. So now I will discuss the main results of this talk, which are the analysis, say, of these pairwise entanglement networks in something called the XX model. Now, the XX model is a model, but I want to justify that it's not just some model that we've chosen for some reason. It is true that we've chosen it because it's analytically solvable, so we can construct these networks for large sizes. But it's also a very important model in modern physics, modern theoretical physics, because it's mappable. Say it's connected to many other fields of physics. So you can find mathematical transformations that map this model into, for example, the Kitaev model that studies Majorana fermions in quantum wires, to conformal field theory, topological excitations in conformal field theory, or to quantum chromodynamics, which studies these strong interactions, or even to quantum field theory in curved spacetime, which is like, say, particle physics in the presence of gravity. And this is why it's also a very attractive model, because in principle, one could extrapolate some of the results that are obtained for this model to this, that might be translated into something interesting in these other fields. I also have to be honest and say that among these things that I mentioned, these three, I really don't know much about the mapping. So in case you were thinking about asking, I will probably deflect the question towards the paper. But if you want to know more about this, I can give you some, hopefully some answers. And there is another point that I want to make, which is that this model, the XX model, was actually solved in 1961. So it's been known, everything that you need to know, I mean, everything you want to calculate about the model, in principle, you can do it. And it's been possible for many years now. But all the things that I will show now, nobody realized them. even though you can see them immediately by naked eye, some of them. And this is because of this is what we are trying to motivate, that this kind of holistic representation of the system can be very useful and can yield new phenomena that otherwise you would miss. But let me first introduce the model a bit. So first of all, what is the system here? The system is a bunch of spins, it's a spin chain. Here I've represented the spins like with these little circles. And there is also a magnetic field. And there are some arrows here, some lines here that represent the interactions. So the interactions are driven by this energy operator. This is the Hamiltonian of the system. And you don't really need to, we don't really need to go through any of this. It's just to say that this term here couples every one of the spins to the magnetic field. So in a way, it tends to align them with the magnetic field. And this other term is pairwise, so between spins I and I plus 1. So it's the interaction term that makes them interact with one another in a certain way. Now, this is the model itself, but we will be studying a particular state of the system, which is called the ground state, which is the state among the states that the quantum system can be in. There is a state with a minimum energy, which is called the ground state. And the properties of this ground state are very relevant for many reasons. And in this case, it is such that when the magnetic field, so of course we will study this as a function of this magnetic field, when you change the magnetic field. And if the magnetic field is larger than 1, then the ground state can be written like this, in the sense that all the spins have their own state, which is pointing up. So if we measure it in the vertical direction, we get the outcome up with probability 1. If we change the magnetic field to a value that is below 1, we get this other thing, which is an entangled state. And I'm not even drawing the empty boxes, but you should understand it's simply that we cannot write the state of each one of the spins separately. It is entangled. And well, this model in the thermodynamic limit, the infinite size limit, it exhibits a quantum phase transition, and it's precisely b equal to 1. And you have this change from not entangled, so separable, to entangled. And of course, I haven't introduced any, say, notation or drawings to represent properly the state of an entangled system, because it's not that as easy as this one. It contains many more terms, but I can still tell you something about the behavior of the system in this regime. So essentially, as you change the magnetic field, you find different states. So the state is not the same for all the values of the b between -1 and 1, but there are many different ground states. And they change, so the state is the same until you reach a point, a value of b, given by some of these bk's for some value of k, in which the state of the system changes suddenly. And well, it happens first at b1, starting from b equal to 1, first b1, then b2, then b3, and the value of the magnetic field is given by this term, writing here the corresponding k. And physically, what happens is that if you measure say that the state of the system is the magnetic field is between B1 and B. So it corresponds to K equal to 1, say. Then if you measure the state in all of them in the vertical direction, you will get something like this, in which one of the spins, maybe this one or maybe this one, is pointing down, but only one. If instead you move the magnetic field, you change the magnetic field and you reach the region corresponding to B3, you will find, when you measure the spins, you will find something like this. So in a way, this K corresponds to the magnetization. So how many spins are pointing up and how many are pointing down. But what we will do now is for each one of these values of, so at this point, when B is larger than 1 or smaller than -1, there is no entanglement. The state is separable, so there's no network. But what we will do instead is to study the networks, the N networks that you have when, well, actually, yeah, let's say the N networks that you have when you change the magnetic field and you go across all these level crossings. And let me start by showing them, just we can see them. Wait a moment. So this is the one that is closest, this is B1, is the one that is closest to the quantum phase transition. And we see that it's clearly fully connected. The links represent the concurrence, and the size of the nodes correspond to the strength, to the weighted degree. When you change the magnetic field and you reach the K equal to 2 Ks, of structure. K equal to 3, you see this structure as well, and so on and so forth. Now, obviously, you see already a community structure, because I don't have to, you cannot keep secret anymore. I mean, it's evident. But then there is a very interesting behavior, which is a nearly zero magnetic field, which is the K equal to 10. So half of the spins, look here, half of the spins point down and half of the spins point up. There is still some kind of community structure that might not seem very evident, but you can see that the weights are not uniform. I will address all this quantitatively later. So what we will do is to study different properties of different networks of this sort, and also to study how the transition occurs from as you change the magnetic field. First things first, let's see, I will show mostly 3 things that were not known about this model. But first, the network measures that we will use are the usual ones. So we will have degree is the unweighted degree. So essentially, we assign a link in the unweighted representation of the network. We assign a link if the weight is different from 0. So it's just we binarize the network. And in the unweighted one, and then we consider the degree. And in the weighted one, we consider the strength. That's the sum of the weights that intersect a node. Then there is the clustering and weighted clustering. We don't use them much, so I will not even introduce them much. But then there is the disparity, which measures, instead, in case you're not familiar with it, it's a quantity that measures the local heterogeneity of the weight distribution of a node. So if you look at a given node like this red one, it has some links intersecting it. And it could be that these weights are all equal, like in the blue node, or it could be that they are very different. And this disparity quantifies this. So if all the links are equal, this quantity is 1 over the degree of the node. And if one of the links dominates over the other, then the disparity tends to 1. And now let's start analyzing a bit the first of these networks, the one corresponding to K equal to 1. So now all that I will discuss in the following this slide and the next one is mostly referring to this one. Here you have the disparity of every node. Well, yeah, that's not true. I will start with discussing all of them first. So here we have the disparity as a function of the node. So the disparity of every one of the nodes. We have a chain of 180 spins, and each one of these ones has the corresponding disparity. And we have different lines. Each one of them corresponds to a different value of K, a different network. And in this first one here, we have K equal to 1. So this is the fully connected one that you see here. And we see that there is no heterogeneity, which is a result that we will discuss later. For K equal to 2, we see that it's pretty flat, but then there is this little bump here. For K equal to 3, we already have this, this regime. And then we see also this plateau here that is a bit higher, and so on and so forth. So as we increase K, we see the emergence of this kind of plateau that has more heterogeneity than the edges of the chain. This, we interpret this as the distinction, the emergence of a distinction between the bulk and the edge of so the entanglement in the bulk of the chain and at the edge exhibits very different properties. This was already hypothesized or kind of shown in some previous publications, but the distinction between what was the edge and what was the bulk, it was never really found. The entanglement, people analyzed the entanglement at the very edge, so the last 2 spins, and compare it to this entanglement in the central one, and they saw that it was different. But what we see here is that actually the local connectivity in terms of the local heterogeneity of the links in the bulk and at the edge is completely different. And then there is this kind of mystery that the disparity of the K equal to 1 case is completely flat. So this would be a trivial result if the network was, okay, it's fully connected, as we know, but if it was like all the weights had the same weight, all the links had the same weight, this would be a trivial result. But this is not the case. If you look at the strength, this is the strength for every node. It's the same as here, but with the strength. And the K equal to 1 case corresponds to this one. And it's evident that the nodes here at the center of the chain have much higher strength than the ones at the edge. So the average weight here at the center of the chain, which is here, I'm sorry, I didn't say before, but the the extremes of so the edges of the chain are these two nodes, and the center of the chain is here. And we represent it like a circular, in this circular layout, just for visualization purposes. But it's clear that here at the center of the chain, the average concurrence is much higher, and yet it has the same heterogeneity. The local distribution is equally heterogeneous everywhere in the chain. And actually, we address the question to what extent is this so? I mean, is it just the heterogeneity as measured by the disparity, or are the local distributions of weight really similar across the chain when normalized? So this is what we addressed. Essentially, we took the different nodes of the chain. We did this kind of numerical experiment. You take one spin here, say this one, and it has k-1 links. So there are k-1 numbers, and these are distributed according to some distribution. Now you normalize these values so that the average is 1. So you divide them all by the mean. And then you have a distribution for these values whose mean is 1. Then you do the same for this spin and for this spin and so on and so forth. And you have a bunch of distributions, one for each node, with mean 1. And now you compare them, or you compare, for example, the cumulative, which is what you see here in this plot. So here you have a lot of curves, and they pretty much overlap perfectly, except for some small fluctuations. So there is this high level of symmetry in this state near the phase transition. And this was not known before. This suggests, and actually you can prove that this is the case, that the weights can be written in terms of the product of local variables, kind of like in the configuration model, but for the weights. And this is actually the case in this model. You can write the entanglement between pairs of spins by assigning a local variable to every spin and then just taking the product of them. But this is only true for k equal to 1. Now, second kind of phenomenon, this has to do with the unweighted network. So this is only at the topological level. What we study is a transition. So how does the network go from the 1D chain, in which is nearest neighbors chain, to a fully connected network? How does this transition occur? What we do now is we draw here, we plot the average degree of the network as a function of k, or k divided by n for that matter. K divided by n simply because k goes in the range from 1 to n. So essentially we want to compare different sizes. So this is the way to represent it. And what we see is that here we have this point here corresponds to the zero magnetic field. So the case in which the network looks like this. So we have average degree 2. And then as we start changing k, changing the magnetic field, we are actually changing the value of k. We have a different network, but topologically they are the same. They have average degree 2. Until we reach some point in which in very few values of k, very few values of the magnetic field, the state changes and the topology changes, and it becomes a network with average degree 4. And if we look at these networks, we see that they are actually second nearest neighbors lattices, second nearest neighbors chains. If we then repeat the same thing and we keep changing the magnetic field, at some point we reach this network with average degree 6, which is third nearest neighbors, fourth nearest neighbors, and so on. So the transition occurs in this way. This, in a way, is consistent, or was kind of known, that it was known that in the thermodynamic limit, as you increase the number of spins and you reach the limit of infinite size limit, the entanglement only depends on the distance between the spins. So in a way, it's kind of expected to get a result like this. But what was never studied is how do the networks look right at these transitions? And this is what we call the topological instabilities. So essentially what we did there is the following. Here at the plateaus, we expect the networks to become degree regular as we increase the size. So they are, like, for example, 1D chain, all the nodes except for the 2 at the edges have average degree 2. For the second nearest neighbors, all nodes have average degree 4, and so on. So we expect that as we increase the size, the contribution to the degree heterogeneity, for example, to the variance of the degree in the network, decreases, because the only 2 nodes that have different degree from the mean, from the others, become irrelevant. And this is exactly what we observe here. Here we have the variance of the degree for a given value of k and different values of n, and you see that it decreases. And it decreases also here and everywhere, but not right at the transition. So at the transition, the networks have some of the topology. They are not degree regular. What they look like is somewhere in between. So here is a transition between first nearest neighbors to second nearest neighbors. And it seems like it is something in between. There are some links. It's like an incomplete second nearest neighbors or first nearest neighbors with some spurious links. But we don't yet understand what's the structure, what are the rules, like explaining this topology. But we call it instability because it only happens at the precise value of the magnetic field. And if you are a little bit off from that magnetic value of the magnetic field, you are in the regime in which you have the degree regular graph. And finally, there is the one related to the communities, which actually includes two things that I didn't separate. So the first one is the evident community structure. Not again, sorry. Yeah. So as I was saying before, it's evident that there is a community structure in these networks for small value of k. And actually the number of communities, it's matches k. So we have 4 communities, 5 communities, and so on. But to be a bit more quantitative, what we did is to use a community detection algorithm, this label propagation algorithm with semi-synchronous update. And we modified it a bit just to account for the weighted structure. So essentially you weight the labels. It's not specific for this model or anything. It's just a community detection algorithm for weighted networks. And when we run it, we see that it works pretty well. Here the colors correspond to the communities as detected by the algorithm. But what's very surprising is that here in the regime in which the network looks essentially like a chain, the algorithm still finds, and as I repeat, we didn't tailor the algorithm, it came as a surprise to us, the algorithm finds precisely the same number of communities as k, as a value of k. So let me rephrase. Here you have in this plot, you have the value of k. So every value of k here is a network. Again, rescaled by n simply because there are different sizes here. And here you have the number of communities detected by the algorithm. And in the case of the weighted network, so the green one, you see a perfect match, except for some fluctuations, some errors in the algorithm. It detects the same number of communities as k. But this is surprising because here in this regime, this corresponds to this plateau that I was mentioning right before, in which this is essentially a 1D chain. So topologically, nothing is happening here. And indeed, when we run the algorithm on the unweighted graph, so we don't tell the algorithm the values of the weights, just a binary network, it doesn't detect anything. It's completely flat until it reaches the transition. But somehow the weights here, that by eye you wouldn't say, or maybe you would, but I wouldn't, they incorporate, they encapsulate the value of k very precisely, even for very large sizes. And the other phenomenon that we realized is what we call these structural classes. Sorry, the structural classes and self-similarity, which I will also connect with the previous thing about the communities. So here what you see is, here we have the network for different values of different sizes, 500, 502, 4, and 6. And what we're doing is we are looking only at the very center of the chain. So this actually corresponds to the center of the chain, the 0. And we're looking at 16 or so spins around the center. And we calculate for each one of them. And what we see is that as you move along the chain, for example, for the n equal to 500, it changes a bit. It has this kind of a periodic pattern. But when you add 2 spins, so 1 spin on each side, you get a completely different profile. You get this green one, which has very different behavior. Or if you like the 504, so you add 2 more, it's even more different. So you have this other pattern here. But then if you add 2 more again, you have this other clustering once again. So it goes back to where it was. Actually, here you can see also these dashed lines. These correspond to adding just 1 single spin. And of course, because it goes from an even number to an odd number, it gets a little bit misplaced, but they correspond to the same. So we've chosen the colors so that they correspond to the corresponding odd one. And the difference between, the corresponding even one. And the difference between is 3. So this would be, for example, 507 and so on. So this blue one is 503. So essentially what we're saying is that if you add one spin, the network at the bulk changes. If you choose another spin, it changes. But if you add another one, it goes back to where it was. So it has a period 3. And here you have a different example. So, but how can we see this more clearly than by looking at these profiles or these spectra? Well, what we do is we take the average of the clustering. Yeah, by the way, we chose here the clustering because the effect is more apparent than with other quantities, not because should be the clustering. You also see this effect with other quantities. But you can take the mean of these values in this region and plot this as a function of n. And then you basically, for 100, you would have some value around here, for 502, something like this, 504, something like this, and so on. And then you see this kind of periodic signals that repeat themselves, obviously. And actually, this orange lines is, this, by the way, does not correspond to this case. Here, the period is 3, here it's 7. But here, the orange lines is our prediction. And our prediction is that this is related, or it comes from the intuition is that this is related to the community structure, precisely, of the network, in the following way. Here, what you see in this plot is the distribution of sizes of the communities detected by the algorithm. So say that you pick one value, this is, I think, n equal to 50, and you pick some value of k, so some of the ground states, one of these networks. And well, as we saw before, the number of communities that the algorithm will detect here is precisely k, so 20 in this case. So the average size of the community, so the average size of a community will be simply n divided by the number of communities, n divided by k, which is this value here. But it could be that, yeah, on average, the sizes of the average community size is whatever value, but it could be very heterogeneous. So you could have many communities which are much smaller than that value and a few that are much higher, much larger than that, but this is not the case. So here, these squares represent the fraction of the communities that have that size. This is the y-axis. So we see that in this case, for example, given this mean, there is only essentially communities of size like around the mean with plus minus 1, say. So the integer part of the mean value and the integer part of the ceiling function of this, or the value plus 1. And this is what we think that leads to this self-similarity. We think that these two things are connected in the following way. I would conjecture, if you like, is that the network organizes itself in a way that it preserves or it tends to preserve this community structure. So when you add a number of nodes, a number of spins that allows the network to, say, restructure itself with the same densities, with the same frequencies in the community sizes, then you have the same kind of connectivity pattern. Let me be more concrete with an example. Say that, imagine you have a network in which you have 2/3 of the communities have size 2, and 1/3 of the communities have size 3. So if you add 7 nodes, then you can add, with 7 nodes, you can add an integer number of communities of size 2 and an integer number of communities of size 3 with these densities, with these frequencies. So that 2/3 have size 2 and 1/3 have size 3. And precisely by calculating this, what is the minimum number of spins that allows you to do this, you find this period. And here you have other examples so that you see that it's not just for small periods. Here you have period 17, and you can, if you want, convince yourself that it actually matches the prediction. And here is period 31. So it seems to be, in some sense, a consequence of the network structure itself, the community structure. I also have to say that this is not working 100%. So we also found counterexamples in which the periodicity wasn't that clear, or what didn't really match perfectly well. There were like some fluctuations, but we don't know if this is a matter of having finite sizes, or it could be also that we are not considering large enough systems. Well, now I've finished explaining the results. Like the take-home message that I want to convey overall is that these entanglement networks are they can be very useful, because after all, quantum systems are very complex as well. And having a complex systems perspective can be very fruitful. And of course, network theory in this case is suitable, because as long as you represent it as a network, and in a way, the network theory was developed to study complex systems. So this is, I think, it's a very good arena to apply networks. And just to mention a few future directions that we have in mind. One of them is to extend all this to this XY model. So the XY is actually the XX is a particular case of the XY model. And well, we want to study this more general case as well as the Ising model. And also this multiplex of dual theories. This is related to the slide I had, in which I was commenting on this mapping that exists between different theories. And we have in mind this idea of using a multiplex in which you have the different theories, the elements of the different theories, and say the same state mapped into the different theories, and understanding correlations, both at the level of within the same theory, but also across theories, say, which is the correlations between layers in this case. We're very much looking forward to study emergent geometry in this case. Also, say, considering my background, my PhD, this is only natural that I start also considering this thing. We are also starting already to work on this connection with the quantum theory in curved spacetime. And of course, an application of this, this is more applied, but we would like to see to what extent this can be used to benchmark quantum computers, like to determine certain correlations that exist in the computer that shouldn't be there, or correlations that you cannot achieve, you should be able to achieve, but you cannot because of the limitations of the device. And also, I want to, now I do a bit of advertising, if I may. So we are launching this QPlayLearn, which is a portal for learning quantum physics and quantum technologies. And it will be ready very soon. So the launching event will be on the 14th at more or less this time. Now it's, yeah, okay, it's more or less this time. Now it's 8 here, so it's around more or less. And you will be able to follow it in live streaming if you like. And finally, let me introduce the team. So these are the core people we work with. Well, Elsie actually doesn't work with us, but we met, this is the Qiskit hackathon organized by IBM, in which we developed this, the tomography algorithm. And we met Elsie there, who studied the PhD here. It is a coincidence, so we work together. But usually it's Sabrina, the group leader, and then Matteo, Boris, and I. So thank you very much for your attention, and if you have questions, I hope I can answer.
Thank you, Guille. That was great. I'm very excited about the quantum A to Z event. I'm gonna definitely check in for that.
This one. You can find the details in the website at some point. They will put them there.
Oh yeah, I'll share that with everybody because that seems really interesting.
Thank you.
Laurent, you have a question.
Yeah, couldn't raise my hand as a host, but there was a question. I was really interested when you started your talk, and you pointed out that in the quantum world, I guess you have to defend the use of complex networks as a way to look at the structure of the problem. And in a way, I think a lot of fields have gone through this, folks who do network neuroscience or network epidemiology. So this could be a new big avenue, and it makes sense that you want to look at the structure. So why not networks? Yeah. But what's your so what can you just give us more details about that experience? How is that dialogue going, and what is the single big argument that seems to work well?
Okay, I think the perspective, I think overall the problem is that quantum physicists are very used to having, say, one quantifier that quantifies something. So the typical questions that people ask is, okay, but this complexity, what is the number that quantifies the complexity? And then you have to argue, no, look, it's a holistic view. It's not something that you can put into one number. There's a lot of information, there's a lot of complexity. So you have to, this idea of studying the network as an object in itself It's something that I think it has to somehow has to be transmitted, and I don't know exactly what's the best way to do this. But I would say this here also it's a field that is very analytical, because many times you can really compute things analytical, have theorems, you have lots of things, and in a way with the networks you don't usually have this. It's a different thing. You don't prove as a theorem this is complex. You have it's a tool to develop, to do an analysis that you couldn't do otherwise, and it's a very, very different thing. And I think for us as people who are used to working with networks, it's obvious the appeal, but not to everybody.
Great. Josh, I think you're next.
Yeah, thanks. That was really great and exciting stuff.
Thank you.
One thing I was wondering is, are there generic constraints in the sense of, like, if I don't specify the network and I just say I have n particles, but I'm going to look at these bipartite density matrices, like, are there constraints on the relationship between those bipartite density matrices in order for it to be like realizable as an n particle state? And then the question is, like, if so, how do those constraints relate to or factor into the states that the network states that you're seeing?
Yeah, this is a very good point. And actually, there are these kind of constraints. There is something called monogamy of entanglement that essentially says that if you have, well, I don't know if I need to show a network for this, but if you have a quantum system that is very, very strongly entangled with another one, it cannot be equally strongly entangled with another one. So the amount of entanglement, if you like, is bounded. So this is something that is, it's, in a way, is one of these constraints. So you have some limitations in how the strengths can be in this sense, yes. And then there is also, I don't know if this is precisely what you meant, which is the fact that this overlapping density matrices that I was mentioning, these density operators, they overlap. So the one between I and J and the one between I and K have the I in common. So the reduced state of I, so if I say this is called tracing out, so if I forget about J and I forget about K, from the row IJ, I get some state of I. From row IK, I get another state of I when I remove K. So the question is, do they match? And approximately they do with this pairwise tomography. So in principle, if you construct everything, you construct the joint, the full state, and then so the one for all the parties, and then you remove the parties until you just take I and J, or until you just have I and K, then it would match. But here, in a way, you are reconstructing them not independently, but they're not coming from the same state. But in any case, you see consistent. There might be small deviations, but if you have enough statistics, it shouldn't be a problem at all.
Great, Manuel.
Yep. Well, that was an awesome talk, Guillermo. I really enjoyed it.
Thank you.
One question. So, is it possible for this network to calculate the entanglement instead of using the concurrence, like using the Renyi entanglement entropies, for example? Have you guys tried that?
Yeah, the problem is that usually what you have, so if you have a system that is closed, so and you have a pure state, so the two systems that you have are in a pure state, then, for example, using the von Neumann entropy or this sort of entropies, then they really quantify entanglement. But if you have a system that is entangled with all the subsystems, then this doesn't necessarily quantify the entanglement, because they can be, for example, classically correlated. So, for example, actually, in this state that I was saying with the first one that Charlie was preparing with the coin, that actually, if you compute, for example, the von Neumann entropy of that class of state, so the ones that Alice and Bob received, you don't know if it's up or down, then they have non-zero von Neumann entropy, but there is no entanglement at all. So this is why concurrence, in a way, is guaranteeing that what you get there is actually entanglement.
Okay, thank you. Thanks.
Olin, did you have a question, or do you want me to read your chat? I'll read it. Okay, so Olin in the chat asks, he says it's not really a question. Okay. But he'd be curious to see how frustration behaves.
Oh, okay. This I have to say, I have to be very honest about it. I don't know. I really don't know. I'm not a spin chain person. I mean, I'm not studying spin chains and actually the physics of this kind of systems. Beyond this, like the network representation, I really don't know much about the phenomena and this kind of things. I'm sorry, but I cannot really.
Laurent, you had a second question.
Yeah, this one is more a question about the science. I really like, you had those three main message that the network perspective contributes to this problem. The first two I loved, especially the second one, the idea that you can look for almost like a susceptibility and find the transitions. The third one, the community structure, the question I have is, are you learning something about the physics, or are you just learning something about the community detection algorithm that you use?
Yeah, this is a good point. But actually we thought about that too, like to what extent. But then we convinced ourselves, and if maybe you will disagree, because we could also have disagreed, but that the fact that you can, with knowledge, so without knowing, say, anything, if I give you, or say if you give me one of these networks, I can determine immediately using this algorithm. So one of these, the case in which is a spin chain. So sorry, not spin chain. I want the lattice. So one of these ones, say some value of k in this range, and I run the algorithm and I can determine the value of k. Then it has to be in a way some kind of physical phenomenon, because it's something I could determine without measuring, say, with only knowing reconstructing the concurrence network and then running the algorithm. I could determine this. Of course, I could also determine it by simply measuring, as I was saying here when I introduced the model. It's simply measuring in the Z basis, so basically measuring in the vertical component. I could already count the spins, and I could do it that way. But in a way, we're learning something about how does the entanglement structure itself? Because the point is that when people study, I mean, there are many things that are known about the entanglement in this kind of models, but usually the perspective is very different. Usually people study, for example, the von Neumann entropy of a bipartition. So you take the system, the whole chain, and you divide it into two classes, A and B, and you study the entanglement between those classes, between these two groups. And this you can do with, for example, the von Neumann entropy or this kind of entropy measures. But this is, in a way, it's very coarse-grained. And this, when people study this more like pairwise quantities, they study correlators and so on, but they never study them in terms of networks. So it doesn't allow you to see this sort of dependence, like a mesoscopic structure emerging. Now, in terms of your question, going back to your question, to what extent this is learning something new about the physics? Well, we call it the physics because in a way, these concurrence networks can be reconstructed experimentally. We even provide an algorithm to do this efficiently. So in principle, it's a phenomenon itself. We consider it as a phenomenon.
And so the answer I got in my mind is like, it would be even more interesting if it wasn't on a chain, right? And then you would be a lot more curious about how entanglement emerges and almost like spread or structures itself, I guess.
Yeah.
Okay, that's very cool.
This is also a good point. And at some point, you can also see already in the image, in the picture I'm showing, that at some point, you have these communities that at some point it stops looking like a kth or n nearest neighbors chain. It looks like something else. And as I said, it's like the networks right at the transition. They have this different topology that we don't yet understand, and this is still worth looking at.
And I just realized I kind of stole Antoine's question in the chat, so I'll repeat it. But Antoine or Tony was asking, how do you expect your results to change or to hold if the underlying structure goes from a chain to a more complex topology?
Okay, wait. Goes from a chain to a more complex topology. This, I have to say, it's also, so you mean that the interaction network, instead of being a chain, a 1D chain, it's something else, right? This, I don't know. And actually, this is a good point. Like, what is the behavior of one of these systems when the interaction pattern, say the interaction network is, yeah. This is a very good question. I really don't know. I don't know what's the phenomenology. I mean, I know that when you change the dimension of the lattice, the physics changes a lot. But I don't know, honestly, if people have studied this kind of systems in more complex interaction topologies. My guess is that I've never heard of it, so it could be very cool to look at. And actually, this is something that that we wanted also to study is the connection between the interaction network and the emergent correlation network, both when you have dynamics or when you're looking at one of these ground states of the system. This is also a very, very interesting field.
Charles, did you want to ask your question, or do you want me to read it out? Let's hear your voice. All right, I'll read it. All right. Okay, he says, go ahead. Charles asks, do you have any intuitions about which kind of entanglement patterns, something other than a chain, for instance, could generate something resembling concurrent networks with hyperbolic geometry?
Well, I wish I did. This is very cool. Actually, I mean, this is one of the things I want to, as I said, this is one of the things I want to work on, like connections with geometry, because they are very obvious connections between entanglement in this kind of systems and geometry. There is something called the area law of entanglement, which essentially says that the amount of entanglement of a region, but again, it's bipartite entanglement. So it's the entanglement of a block, of a group of subsystems with the rest. The amount of entanglement grows as the area of the region. This is one of the main results that, but this is, of course, it's a connection between the entanglement of the system and the geometry the system lives in. But there are also less obvious connections between, actually, for example, the entanglement in some critical systems has been connected. So critical, as in exhibiting phase transitions like this one, has been connected with the ADS-CFT, this anti-de Sitter conformal field theory mapping in the string theories and these sort of fields. And it's essentially also connected to the fact that the entanglement of a region depends or behaves as the area of a region in a space that is curved, as in hyperbolic geometry. So I don't know, but this is not at the level of concurrence. It's at the level of the block, say the whole set of systems and the rest of them. But I don't know if there are networks in which the entanglement at the level of concurrence of the bipartite one can exhibit this geometry. This would be a super cool result.
Very cool. Any other questions from the audience? All right. Thank you so much, Guy. This was awesome.
Yeah, thank you very much for having me here. It was very nice.
It was nice to see you. All right, everybody give a clap. You can unmute yourselves if you want.
Thank you very much.
Thank you all for being here. We'll see you in a couple of weeks for a talk on archaeology.
Wow, very cool. See you.